Okay, some comments about the projects. I graded them, and you're going to receive scanned pages via email. I make this recording because you will have to continue to work on the project. It is an important part of the grade, of your grade, and in the past, the letter grade for the class of many students was was boosted by the final project report grade. Okay, so what I noticed was that a few observations that refer to or apply to a number of you. Not following or reading carefully the grading sheet, not having a reference list and referring the references in the text, equations that were not numbered, and number to an equation goes to the right, just parentheses, equation number, just 1, 2, 3, and 4 close parentheses. For the figures, we have the caption below. For tables, we want the caption to be on top. This is here to illustrate a different thing that I want you to pay attention to. It's called ink to paper ratio. So you have a graph that is what we care about for that plot, but you have a lot of blank space. So edit the limits, minimum maximum limits over the s-axis in this case to where the graph is shown in more detail. And then another thing that I've noticed, if Excel adds its own title to the graph, take that off and limit to just it says on the caption. Have a caption and do not repeat the what Excel already does. Okay. So back to the project specs. There is some aspects I want to emphasize further. So on the introductory part, find relevant information. Don't make that introductory part too long. If you find patents, make sure that they are relevant to the architecture of a press that we discussed, a simple crank-driven press. Go back to your manufacturing processes book and read on metal forming, punch presses, and the like. Okay, the other thing that I would like to point to is not knowing how to format properly the text. So don't allow for large spaces. There are ways of keeping paragraphs together. For example, if I want notes to stay together with the if I want the text notes to stay together with the rest of the text, I just click on and then go to paragraph. So again, I click on this, go to paragraph, and line and page breaks, and say keep with next. Okay, so watch what happens. If so this, and I'm using all the time this indicator of the formatting. So this little square indicates that this paragraph will stay with the others. And of course you can extend it to multiple paragraphs. Okay, I can have these two stay with the rest. So I delete one and they are still together, another one, and only now they switch. They jump to the previous page. Okay. There are ways if you want. So say I have an equation a plus b equals C. And of course use the equation editor that goes insert an equation. Well, I skipped that part. If you want to the equation numbers to be at the same alignment, so have a tab, click on this. I'm looking at well, I'm not full screen, but look at this, and you can toggle it between. I usually stay with this one, this type of stopper. And so I have a tab, and I click here. Okay, and now I can put equation number, and then okay, so they will be at the same level. And I think this is about it about that I wanted to say about formatting. Again, make sure you observe the grading scheme here, and do not modify my my cover page. If you have suggestions for improvement, let me know. I may do it for the final final project report or for future semesters. Okay. The next part of this recording will be about what you'll have to do additionally. So now that you have an electric motor determined, that's number 11, select a three-phase motor. So you know for that motor, you know the power and you know the RPM. Very likely you have a synchronous speed of 1800. Nominal speed will be maybe 1750 or so. You will have to design or select the pulleys and the belt for the press. If you go to this photograph and the schematic to the right, so you have as you can see, you have a motor, although I'm asking you to place it at an angle, not on top. And this is the pulley on the motor shaft. There is a custom-made pulley. This is not off a catalog. That is part of what appears to be a brake system. So then there you have a pinion driving a gear, and the gear is mounted on the crankshaft. And this would be, although there's inertia in other of the moving parts, including the motor shaft and the rotor of the motor, but this will be the main inertia, rotational inertia. And we want to size, again, we want both the gear and the belt, with the belt being first. And what I'm going to do is to make this slightly bigger. So let's reverse engineer for just a little bit and see what we have. So I'm taking a screenshot, and I go to Paint, and so I have Paint, and I want to center Paint and say Paste. I already prepare a ruler, you will see. Actually, I want a little bit bigger. So I'm taking a screenshot. Could have prepared this ahead of time. So Alt Print Screen, and then go to Paint again, and undo, and Paint again, paste again. Okay, we'll stay with this. And so let's see what is the possible gear ratio that we have. Like we enlarge this, let's see. So I have it like so, and cut, select all, delete, paste, view and make it double. Okay. Alright, so I'm using the ruler to try to take some measurements. So I go this way and I go transparent, and I'm measuring here. So what appears to be the pitch diameter of the gear is 50 millimeters, and then for the pinion, the pitch diameter is, okay, I changed my mind, I'm going to make this non-transparent. So, and this one appears to be maybe 8 or 9. So transmission ratio is 50 to 9. Okay, so I have transmission ratio right here, I equals 50 to 9, which is 5.56. Okay, and this is for the gear. And I'm not done using the ruler. I'll go and measure the transmission ratio for the belt transmission. So the pitch diameter of the sheave is maybe 18 millimeters. So I have 18 millimeters. Again, for the belt, I belt is going to be something divided by 18, and then need to measure the diameter of the driving pulley. So this is more like maybe 40 millimeters, 42. Okay, so I have, say, 42, wrong tool, 42, and so this goes, this is going to be the transmission ratio at the belt, 42 over 18. Again, 42 over 18 equals 2.33 transmission ratio. All right. So 50 over 9 and 42 over 18 for the gear and for the belt. Just orientatively, let's see what others have done. In the notes, so I have the chapter on belt, chapter 7 from the book by Mott, and I have the chapter on gears that we covered, first part of the chapter on gears. And in the chapter on gears, towards the end, we had a table of characteristics of gear transmissions. So it says, would be our case, straight spur gears, a minimum number of teeth for the pinion, it's without addendum modification is 17 or 18, and usual gear ratios go up to 6 to 1. For the belt transmissions, if you study the chapter, so there are some limitations in terms of the speed of the belt itself. It's recommended to be around, yeah, there is a limit here, but it's recommended to be around 4,000 feet per minute. And then when it comes to transmission ratio, there's also recommended to go up to 6 to 1. If it's bigger than 6 to 1, the angle of rep on the small sheave is going to be small, and you need large amounts of tension in the belt. Okay, so a large amount of tension in order to provide for the force in the taut belt to be transmitted. I'm looking for the paragraph, should have bookmarked it, but here too, it's where it says that the maximum transmission ratio for a belt drive should be 6:1. Don't know exactly what it is. It's somewhere in the text. Anyway, so it is within the reversed engineered from the project specs drawing. It's actually a CAD drawing, 3D model. Follow those recommendations. Now, for your particular project, where you have selected a transmission ratio, or transmission ratio ultimately, you selected an RPM for the crankshaft, and now you have a motor, so you know the RPM of the motor shaft. So say we go from N of the motor, keep on clicking on the wrong tool, N motor, say 1750 RPM, and we have N of the crank, that's between 80 and 120, so let's say 80 RPM, corresponding to punches per minute. Then how do we divide between the gear reduction and the belt reduction? And so the total transmission ratio now, it's, in our case, it's going to be I total. It's going to be the input speed at the motor shaft and the output speed, which is the crankshaft, over 80. And this is equal to 1750 over 80. This is equal to 21.875. All right. If I take the square root of this 21.875, I can get the transmission ratio, theoretical transmission ratio, will be equal to distributed between the gear and the belt. So I theoretical of belt, when it's equal to I of the gear, it's going to be 4.677 in this case. So of course I cannot get this exactly, but I can get it close, and I don't have to make the two equal, but I have like a middle value from where I can move in both directions, either making smaller or bigger for the gear or for the belt. All right, so I have 4.67. It's less than 6, which is maximum recommended for belts. It's less than 6, maximum recommended for gears. Now we know another thing. We know that the minimum number of teeth of the pinion should be, it says 14 to 17, actually 18, maybe slightly bigger, results in stronger teeth ultimately. We could try to count teeth. Actually, this drawing here allows us to estimate the number of teeth of the, and this is an actual punch press, so we could go and, well, I'm not going to do it in detail, but we can go and open this in Paint, and we can find somehow where the middle of the, a diameter of the gear would be, and I'm counting the teeth on one side, make it double, and I can approximate how many teeth on the gear there are. Anyway, so for the starter, we can assume the number of teeth of the pinion to be, say, 18, although you can go bigger than 18. So let's say it's N of pinion, or N1 equals 18 teeth. And if I want to go with this exact number, 4.677, if I multiply by 18, I get, so N2, that of the gear, would be 84.187, so either 84 or 85. Okay. We can go with bigger than 18, I said, so we can go with 21 times 4.677, so that will be 21, I said, and teeth here would be 98 teeth. Okay. And now we can look at, and remember, the pulley would be custom made. So you're going to, if you're to design this press to the last detail, you'll have to generate mechanical drawing with tolerances and everything, material selection for the driven pulley. The one on the motor shaft should be, it's much more economical to just select one that is ready available from manufacturer, from catalogs. Okay, so let's go again and write the total gear ratio, I total. So I have I total this is equal on one hand to, let's stay with the left, so it would be 98 over 21 times would be diameter of the large pulley over the diameter of the small pulley. So pitch diameters would be P, also standing for pulley, and we can also, given the total transmission ratio 21.875, I can now get the I of belt as being 21.875 divided by parenthesis 98 over 21 equals, and so what is this equal to? 875.75 over 98 times 21. So this is 4.6875. And it doesn't have to be exactly, and of course you can always come back and consider, instead of 2120 number of teeth, and adjust slightly this ratio. But otherwise, for the belt design, the target transmission ratio would be, under the circumstances that I considered, again with 28 or at the 98 for the gear and 21 for the pinion, would be 4.6875. Okay, so we can go to the book by Mott, and I'm advising you to read it carefully. It's not going to be, I'm not going to lecture about it. It's very well explained here. the some background information, like what tangential velocity, angular velocity, how they are related, something that you know from dynamics. Common to both belt and chains transmission, including flat belts and other than V belts. For your project, of course, the belt could be multiple belts, but will be a V belt. And there's some geometric relationship between the center distance, pitch diameters of the pulleys, length of the belt, and angles of wrap, which you, by the way, repeated slightly differently for the belts. Again, our punch press will use this type of belt, the V belt. There's a pitch diameter, which is not the root diameter, is not the outer diameter, somewhere in between, that is used in kinematic calculations, how to calculate the angle of wrap, and then span, that's the span of the belt, that's this distance from where it breaks off the pulley and it between the tangent points. And so there are various sizes, the smaller ones. There are for our case, the candidates will be 3V or 5V, either single or multiple belts. And there is a sample problem that you are going to follow, really. There is recommendation how close the axis of rotation of the sheaves to be. It's as this recommendation here. Belt speed, remember 4,000 feet per minute is the average preferred, with can go above that, but not less than 1,000, because it could result in slip and require too much. So a slow belt that transmits a given amount of power would require larger friction. Anyway, so it's a selection chart that tells you based on the design power, and you'd have to correct the input power of the motor with a service factor, and ours would be moderate shock loading, and 2 shifts a day would be maybe 1.5, rather 1.3, 1.4. Okay, so follow the procedure in the chapter, and I started saying that there's never got there. There is a sample problem, really, which would be so sample problem 7.2 is the one that you would be following. So you begin with the horsepower that you want, the RPM of the motor, and 2 shifts a day, maybe, and then again, instead of RPM, the transmission ratio between the motor shaft and the pinion, and that was we wrote it down 4.6875. So I take this number and multiply by 1750, rather divide 1750 over 4.6875. That's 373. So input RPM 1750, output RPM, that's the RPM of the pinion. 373 would be, for my case, working 2 shifts a day. Again, you choose. I'm not telling you how many. I know it's easier when it's unambiguous, but you need to make some decisions. Is it going to be used 1 shift a day or 2 shifts a day, in terms of duration of operation? And otherwise, follow the steps. Sheaves come in certain sizes, and if you're to use at least one, and you will for the motor shaft, that is a standard sheave size, and they're here in these charts that allow you for making correction to the power that the belt can transmit. There are several corrections based on the angle, wrap, and length of the belt and such. And here you see the sheave sizes. Okay, so there are sheave sizes available as well as elsewhere on the in RPM of the input sheave or input shaft. So you can of course consult online literature catalogs of sheaves, but the short message here is to just follow sample problem 724 for the design of the selection of the sheaves and selection of the belt. Again, you might end up using more than just one belt, and very likely yours will be either 3 V or 5 V. Okay. Again, this was for number what step was it in the project? This was for number 12 step in the project. You are going to then calculate the pair of gears. Remember, mine were 21 and 94, and so that will be number 13. Again, following some sample problems I'm going to tell you about, and then there will be shaft design, bearing selection, and then you need to do a mechanical drawing, carefully done mechanical drawing with tolerances and dimensions for the pinion shaft. Essentially, this part of the press, which is supported on 2 bearings. You're going to select those bearings. All right. So this being said, I'm going to stop recording.